Let's do a slightly different example for partial fraction decomposition, where we have 16x squared plus 6x minus 9 over x cubed plus x squared dx. So to do this type of problem, we need to first say, all right, do I need to do long division? So if I look at that, I say, well, the degree on bottom is actually greater than the degree on top, so I don't. So thank goodness. So the second thing I need to do is I need to factor the denominator. So I'm going to say x cubed plus x squared. Now what does this have in common? Well, this has an x squared in common. So x squared x plus 1. Okay, so then what I have to do is I have to separate the linear factors. Now when I look at this, I look and I say, okay, that's a linear factor, but that looks like a quadratic factor because it's got an x squared in it. Well, it turns out it's actually not. And the reason that's true is if it's just a bare x, what that is that's actually a linear factor with a multiplicity of 2. So that's just an x, but the actual multiplicity is 2. Now you actually, I believe, could do this particular thing as a quadratic factor. If it was x cubed, you really wouldn't want to do it like that, but I think you could do this as a quadratic factor, but why would you is really the question. It's kind of a waste. So the answer is basically don't do that. So I have a linear factor with multiplicity 2 and another linear factor. So what I need to do here is so then it's, all right, a over x. So we do the linear factor with multiplicity 1, and then we work our way up to the total multiplicity. So again, if that was cubed, it would be b over x squared plus c over x cubed. So we just keep going up to the multiplicity. And then we have this linear factor. We don't have any quadratic factors, thank goodness, so we can keep on rolling. So now we need to solve. So to do that, we need to multiply by the denominator, multiply by this on both sides. So I'm just taking this and I'm multiplying by that term, multiplying by that denominator. So in doing that, I see I'm always going to cancel the denominators on the left side. So you should always be left with just the numerator. On this one, only one x cancels, so I have a, x, x plus 1. On these, both x's cancel, so I have b, x plus 1. And on these, just the x plus 1 cancels, so I have cx squared. Okay, so now I've done that piece, I need to do part B. I need to pick convenient values. So one of the convenient values, since I have an x there, is I can just pick x equals 0. I say, all right, well, when x is 0, I get 0, 0, negative 9. And then this term disappears. This is b. And that term disappears. Well, that's easy, right? So b is negative 9. All right, let's keep on rolling then. Now, what I want to do is I have this other factor. So I use the one that cancels the x's. Let's use the one that cancels the x plus 1s. I can say x equals negative 1. So that's going to be positive 16 minus 6 minus 9. So positive 16 minus 6 is 10. Minus 9 is 1. So I end up with 1 equals, that disappears, and then negative 1 squared is 1. So c is 1. So b is negative 9 and c is 1. Well, that's pretty convenient. So now I'm going to say to myself, how do I cancel b and c? Well, if I use a negative 1 to cancel b, it cancels a. If I use a 0 to cancel c, it also cancels a. So I can't just use 0 and negative 1. And that's okay. So what I can do is I can do something not quite as convenient, but not terribly inconvenient. So let's pick something like x equals positive 1. So if I pick x equals positive 1, I get 16 plus 6 minus 9. So that's 16 plus 6 is 22, minus 9 is 13. So a times 1 is a times 2. So I have 2a, b times 2, so 2b plus c. So 13 is 2a plus 2b plus c, which doesn't look very helpful except for the fact that I know what a and b are, or b and c are. So I can say 13 equals 2a plus 2 times negative 9 plus 1. So 13 is 2a minus 18 plus 1. So if I add 18 to both sides, that's 31. If I subtract 1 from both sides, that's 30, giving me that a is 15. So I now have a, b, and c, so I can plug this into my original equation. I can say this here is now the integral of, sorry, I'm using this over here, a, so 15 over x plus negative 9 over x squared plus 1 over x plus 1 dx. So there's something you're going to want to be careful of here. The first one, 15 over x is natural log of x with the 15 in front. But and this over here is a natural log. But this isn't a natural log, right? Your partial fractions condition you to think, oh, natural log, natural log, natural log. But not everything's natural log. This right here, oh, this is a power rule. That's like negative 9 to the x minus 2. So we add 1 to the power, so it becomes x to the negative 1. Divide by that power, so divide by negative 1. So that gives me a positive 9 over x. So be careful. Be very careful. It's a common mistake. And then over here, I just get the natural log of x plus 1 plus c. And that's really how you do it. You just, again, you have to watch out when those multiplicities happen because you're conditioned to think about logs, but it's not logs. It's actually the power rule.